Here is a treatment of electrochemical cells. We're going to separate the oxidation half reaction from the reduction half reaction in an electrochemical equation and use the current that develops to do some work. This is our history of electrochemical cells. It goes back to Luigi Galvani in the 18th century, and this is his testimony. He was actually working with frog muscles, and you can read that if you'd like. But what it comes down to is, what he did was that he took two different metals and he immersed them in a saline solution, connected them by a wire, or touched them to a muscle, and developed an electrical current that made the muscles twitch. We now know that a small amount of each metal was dissolving in the salt water to make the corresponding zinc and copper ions, and it formed an oxidation-reduction reaction where the oxidation was separate from the reduction. He had made an electrochemical cell. The zinc was being oxidized, as you see here, and the copper ions were being reduced. And he made the electrons flow from the zinc to the copper ions through, in this case, the frog muscle. And the muscle then twitched from the stimulus, and that would continue, of course, until it ran out of ATP. Typically, we would see an electron transfer reaction all occurring in the same place. For instance, if you took zinc metal and immersed it in copper nitrate solution, you would eventually see copper depositing on the zinc as the copper ions were reduced to copper metal and the zinc metal was reduced to zinc ions. In the case here, the zinc came directly into contact with the copper ions in solution, electrons passing directly from the metal atoms to the ions. But in Galvani's reaction, he separated the reaction into two half reactions using the salt water and the animal muscle. So the electrons were made to do some work before they got to the copper ions. You may recall what an activity series is. This is one that we developed, or that you can develop experimentally. Elements on the top of the table will react with ions of the elements below. So to give you a good example here, to give electrons to the ions of elements below, zinc, for instance, reacts with hydrochloric acid. So zinc would react with hydrogen ions to make hydrogen gas and zinc ions. Calcium will react with hydrogen ions in an acid, or even in hot water. Copper, which you can find on top here, will react with silver ions. Now, can we quantify this reaction? Well, Alessandro Volta gave us the method for doing that, and he created something called a voltaic cell. What he did was he alternated strips of copper, water-soaked cardboard, and zinc. So copper down, then cardboard, then the zinc, then the cardboard, then the copper, then the cardboard, then the zinc, and so forth, and found that the more cells he made of copper, cardboard, zinc, the higher he measured the electric potential, or driving force, and the more cells he made, the higher was the potential. And we therefore call this driving force voltage, using his name. This is a diagram of an electrochemical cell, and any electrical device can be placed in the circuit here. A voltmeter, or for instance a light bulb is frequently used. You can see the zinc is losing electrons to the copper ions over here, but the electrons have to flow through the electrical device in order to get to the copper ions. In the middle we have a salt bridge, which could just be a piece of filter paper that is soaked in a saltwater solution. what's happening? Electrons are produced in the oxidation reaction at the zinc-zinc ion interface. This electrode is called the anode. Oxidation occurs at anode. Electrons are pushed through the conductive wire and through the work device, a motor, a light bulb, a voltmeter. And at the cathode, the electrons will collide with copper ions that are attracted to this place where there is negative charge. And the electrons will reduce the copper ions to copper metal. The sulfate ions here in the two sides then can migrate through the salt bridge, and the zinc ions can go in the opposite direction so that the charges will be balanced. Now, we have made a number of electrochemical cells, and each half cell measured against the standard half cell, which is hydrogen gas and hydrogen ions at 1 molar solution. Each one of these actually gives a predictable voltage. You can do something similar with the metals and a lemon if you wish. Some labs do this. I like to do that. And so when you measure against the hydrogen and you have an iron electrode with iron 2+ ions available, you get a negative 0.44 volts. When you measure the hydrogen electrode against the silver ion silver, it gives a positive 0.80 volts. So, given this table, let's calculate the standard voltage of some full cells, two half cells together. You'll notice that we put the ion first, and then this slash separates it from the metal, or the oxidizable item, species. The double line represents the salt bridge, and then what we are going to reduce, in this case the silver ions, and a slash, they would be in contact with the silver atoms in the other electrode. Now, if you do this, you will see, here's your 0.44 volts, and here's your silver. I like to think of this as we're really calculating the distance between this electrode and this electrode. And the hydrogen electrode is right in the middle. So if you take this and subtract the oxidation, because it's an oxidation, you have to turn it around, you can either subtract minus 0.44 volts from the 0.8, or you can change the sign and add them together. Either way, where the oxidation is occurring, you're going to have to change the sign on this if you're going to add it to the electrode half reaction where the reduction is occurring. So 0.8 minus a minus 0.44 is 1.24 volts. Now why don't you do this one now that we've shown you how, and then we'll check your answer after you turn the video back on. We say 1.2 volts. Here's the lead 2/lead 0.13, and here's your bromine bromide. This is of course where the reduction is going to take place. This is where the oxidation will take place. So you're going to take 1.07 and subtract a minus 0.13, or change the sign and add, and that's why you get 1.20 volts. Let's do one more with the copper 2+ copper and the lead dioxide lead 2+. Turn the video on when you have solved the problem. This is 1.12 volts. Now notice, this is where our oxidation is going to occur. This is where our reduction is going to occur. We're going to have to change the sign here and add. If we now change this to minus 0.34 volts and add it to 1.46, that's how we get 1.12 volts. So we can predict the force with which electrons are driven from one half cell to the other. And this, of course, is what we would measure with a voltmeter, say in an automobile. So the shorthand diagram oxidation reaction is given first, the product on the left and the oxidized species on the right. The reduction reaction is second, with the reduced species on the left and the product on the right, and the salt bridges in the middle. Now, how do dry cells work? Well, this is a typical old-fashioned dry cell type battery. The inner half cell, we've got zinc and zinc ions, and they're connected to the central post. The electrolyte inside the case is a gel. It's got ions in it. It's got your migrating ions. The outer half cell could be, say, a copper top, where you have copper with respect to copper 2+ ions inside. That's connected to the outer post. Here's a cutaway of a dry cell battery. And that's our little talk about electrochemical cells.